welcome to this today's session of Saturday Talk by JanyuTech. We are privileged to have Mr. Prakasha Rao, sir, today for today's session. A brief introduction of sir. Mr. Prakasha Rao, PJVKS, retired as an outstanding scientist in Indian Space Research Organization, that is ISRO, and was serving as Director, Space Infrastructure Program Office at ISRO Headquarters, Bengaluru. Just before reporting retirement, he was reporting to Chairman of ISRO. He briefly held the additional charge of Director, DSRQ, at ISRO HQ. Prior to this, he has served as Program Director, LEO and Planetary Platforms, and Deputy Director, Spacecraft Reliability and Quality Area at UR Rao Satellite Center. Earlier to this, Mr. Prakasha Rao has served as Project Director, GSAT-9 South Asian Satellite, GSAT-17 and GSAT-18 Communication Satellites. Today, he is going to speak on the topic that is space environment. Over to you, sir, from here. Thank you so much.
Okay, thank you for the introduction. This is my third or fourth lecture at JanyuTech. First, the topics that are being covered are why study environment for a spacecraft, classification of various environments, and for every environment, what are the contributing factors, typical characteristics of that environment, and what is the effect on our hardware, and how to mitigate, and some examples which we have seen the examples of those things, and how to simulate for that particular environment, what are the methodologies that are there. This is how I am going to cover. I think this will be useful for any product. It need not be for a spacecraft alone. Any product, if you are developing, the most important aspect is understanding the environment. Though I think one of my lectures earlier have told, but still I will tell you one anecdote where suppose I have shifted my house from Rajaji Nagar to Rajarajeshwari Nagar. My son has gone to school. By afternoon, the school principal, new school in Rajeshwari Nagar, the principal has called my wife and she told that your son is very naughty. He is disturbing all other students here. Teachers are very much upset with him. Then my wife told, no madam, he is a very good boy. He has so much liked by his fellow friends at school as well as his teachers. What happened is actually we have shifted from Rajaji Nagar to Rajeshwari Nagar. So maybe here the neighboring kids and all whoever are there around my house, they are very naughty. He used to go to playground to play with them. So joining them, he has become naughty like that. So don't worry, when his father comes back home, I will tell. He will be setting all right. So don't worry. Like that she told to the principal. Evening he has come back home and went to play with the children who are in the neighboring ground. And that neighbor, along with neighboring children to the ground, he has gone to play. By night, after half an hour, all the ladies around my house, they have all come and knocked my door. And they told, your son is very naughty. He is disturbing all the people here in the ground and he is taking panga with every word. What is this? Like that. And she told, no, he is a very good boy. All our neighboring children used to like him so much. Today he went to a new school. Perhaps that school environment has spoiled him. So that is the impact the environment will have on any product. So if we take even space history, many of the on-orbit phenomena, if you see failures when they were analyzed in a particular period, out of around 3,000 anomalies, 20 to 25% are traced to anomalies which are directly related to the environment interaction. Either the environment was not understood correctly, or it was not designed for that environment, or it was not analyzed for the environment, or not tested in that environment. So it's very important if you are developing any product to see that we are able to understand the environment first, and then the impact of that environment we have to understand, then design for that environment, analyze, and then test before we put the product for use. Otherwise, we are bound to see some failures. So though considered perfect vacuum, space still contains significant amounts of neutral, ionized, charged matter and electromagnetic radiation. And this particular matter has got a very good potential to interact with the spacecraft elements and impact mission effectiveness. And it can limit the life of some of the hardware. And prevention is, so just studying what is the use, because if you study it, we should be able to possibly mitigate the effects. And also it will provide inputs for the environmental design, where you cannot design the equipment for absorbing that environment. Then it should be possible to design at least to see that it is insulated from the environment. That is also one of the ways. Suppose temperature is one thing. If you cannot design for the total range, at least we can see that thermal design we can do in such a way that we are keeping the equipment within its margins. So it forms a basis for material selection and evaluation, and also testing and evaluation of various subsystems. It is good to understand the environment, because apart from functional testing, it is environmental testing forms a major part of any system testing. And it has become so much important, it has become that NASA formulated national program to coordinate the studies related to space environment, and ISO Space Systems Committee also was formed to address international standards for the environment. And at times, there are some environments which are not always harmful. There are some of them are gainful also, which we can use it to use. We can use gainfully for certain particular aspects. So if we talk about for a spacecraft, the environment can be classified into three major things. One is the pre-launch environment. Before launching on the ground, whatever we are doing, it could be during the transportation or during handling every day during the regular at the ground testing, and storage also. Even after we make the spacecraft ready, sometimes the launch may take place after a little while. So the storage conditions. So in a pre-launch environment, the major factors will be temperature, humidity, electrostatic discharge. Even the clothes when you bring up from or just during certain seasons, we can see that if humidity is less, we will get a slight shock. Correct? That is due to the electrostatic discharge. So that is ESD is another environment. It is prevalent in ground also, and there is another kind of ESD in orbit that we will also discuss. And particulate contamination. See, because we are having some of the equipment which need to be assembled and operated in a very clean environment. So unless they are so for that, either we have to seal those equipment and all those things. But while doing that fabrication and before sealing and all, the contamination control is another important aspect as far as pre-launch environment is concerned. And with respect to launch, when we do, this is the actual period of the rocket flight to go to the space. While taking spacecraft into the orbit, the rocket itself will be taking, or launch vehicle will be taking it to the orbit for 20 minutes or 30 minutes, whatever. So during that time, again, the temperature, and as we are going higher, the decreasing pressure, then the acoustic noise which is associated along with the spacecraft, the random vibration which are and sinusoidal vibration shock which happen during various stage separations, and actual spacecraft separation itself from the launch vehicle is a major shock inducing environment. So all these aspects have to be considered. And of course, sustained acceleration. As the vehicle is moving up, you are having a steady G and not steady, it will be actually acceleration will be going up also, because that's how you are going to escape the Earth's gravity and move ahead. So all this all these things have to be accounted while designing for the spacecraft. And the most important of all, of course, all are important, but this is the most because a spacecraft is going to live in that environment for 15 years. If we take a geosynchronous orbit, the spacecraft has to operate for 15 years without being attended to. That is the major challenge as far as spacecraft is concerned. So for 15 years, it has to work in this unknown environment for 15 years without being attended to, except for some regular housekeeping operations. Some commands may be given, but we can't go to the spacecraft nor access it nor repair anything like that. So under the orbital environment, the obvious thing will be the weightlessness, which we see always in any space station and all. If we see the kind of struggle that astronauts will be going through, so the microgravity has got its own impact. Vacuum, temperature, neutral environment, plasma, radiation, micrometeoroids and orbital debris, which is much being talked about these days, and the magnetic field itself, the residual magnetic field actually, because as you go away from ground, the field will be inversely proportional to the inverse square law, so inversely proportional to the orbital height, and all other aspects like EMI, EMC, sun-moon inclusions, structural interactions, all these things have to be done. So with respect to weightlessness, when we take, what are the contributing factors for the weightless? This is it is the balancing of gravity by centrifugal force, because spacecraft is orbiting around the Earth, so results in 0 G or near weightlessness. So that is the factor which contributes to the weightlessness. And what are the characteristics of the weightlessness? At 400 kilometers, 88.8% of its gravitational field still remains. So absolute weightlessness is experienced if sum of all forces is 0 at all points of an object. Not practical due to finite dimension of spacecraft body. Okay, there is a theory around that. But what are the effects basically? We have got some deployment mechanisms in the spacecraft. Their behavior will be affected, because in ground when we are doing, it is all at the G level, we are doing all the assemblies and all, but in spacecraft it is 0 G. So all our ground testing, because you cannot design your hinges and all to withstand 1 G and all, because it becomes an over design. So weight is another important factor. So we will not be doing doing the over design. So then how to test it on the ground? So that is an important aspect. That's why we are having zero-G simulators, all those aspects. Then hydrostatic and hydrodynamic effects on liquids. How a liquid behaves in a weightlessness will be entirely different from when G is there. It is pulling the liquid and it is having a formal shape. But once it is not there, if there is a little bit of vacuum space empty space in the tank, the liquids will be sloshing. So even our tankers, even milk or let's say petrol tanker or anything, if you take, which carry these fuels, after the slosh effect is a very, very significant aspect once you empty it to some extent. Even if you carry one pot itself with water, if it is half filled pot, the slosh effect can be felt. Then severe and under vacuum, it becomes worse. Severe implications for under weightlessness, it will become worse. Severe implications for manned missions, which is because human body, we are designed for G environment. So all our naturally, which we think very effortlessly on all the activities, right from the time we get up till we sleep, whatever we do so effortlessly on ground will become a very, very major activity when you have to do it in the space. Accordingly, the systems have to be designed. Then frictional characteristics, because of the bearing, lubrications and all those aspects, when the G is not there, so those frictional characteristics, they have to be seen, and partly restrained and free motions, and liquid heat transfer mechanisms will be impacted, and it imposes test limitations like solar array drive assembly, which we test on ground. It is difficult to test it because the zero-G simulations and all those things are difficult. Otherwise, the solar array drive will be the bearings, the slip rings will be transferring 10 to 20 kilowatts of power, which is generated on solar panels, into the spacecraft inside all the electronics. So this will happen through slip rings and all those things. So those testings and all, weightlessness imposes some limitations. We overcome by various techniques. Okay. So mitigation techniques is, with respect to slosh, you cannot do anything on ground, but it has to be modeled and the impact has to be studied. That is what they do for propellant tanks and all. And of course, there are some vanes and all they will design to reduce the impact of the slosh. So this is where a lot of mathematical foundation is required. And we have to design for zero-G loads, of course. Design has to be, and training of crew. That's why they spend years to train a crew because of the zero-G, they have to get used to that. So for that, various simulation facilities are there. So training of crew is another important aspect. And baffles and vanes to dampen oscillations due to liquid movement in the propellant tanks. So these are all with respect. But with respect to electronic hardware, if you see, the impact of weightlessness is not much. It is only for it's not there actually, not much, it's not there. But it is mainly with respect to mechanical systems, bearings or hinges and all those designs. So there we have to account for the weightlessness environment. And with respect to simulation or evaluation methodology, if you see, zero-G simulation is for mechanisms. Testing in aircraft scale model of tank simulation, this is for parabolic flight path when you are there at the vertex, there we can get zero-G. Even in giant wheel when we go, just when we are about to change the direction, we will be feeling a zero-G effect for a very, 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 very short duration on ground. But there are ways to simulate like that, where you take it on a parabolic flight path and try to test certain systems. So that is one way, but otherwise, in general, zero-G simulation is quite involved. Then the most predominant environment especially for electronic systems and all, what we have to consider most is the vacuum. Because here the contributor factors are, electronics means not directly as electronics, but vacuum has impact on temperature that will in turn affect any electronic device. So pressure drop with altitude. If it's at sea level, of course, we all know the pressure is 760 mmHg. That is 1 mmHg we call as torr. So 760 torr. And in terms of mean free path, at that pressure, the intermolecular distance is 5 into 10 to the power of minus 4. That is 0.5 mm. So between two particles, the distance at sea level is 0.5 mm. But as you go to 200 kilometers, the pressure will drop to 1 into 10 power minus 6. And the mean free path is 50 meters. Why this mean free path is important is because when we want to simulate vacuum, it is that mean free path which we have to simulate. So at 900 kilometers, if we go 10 to the power of minus 6 torr is the pressure, and the mean free path is something like 500 meters, half a kilometer between two molecules, the distance. So at 10,000 kilometers, You can see it's almost you cannot see the distance. So typical characteristics of high vacuum of infinite pumping capacity. So the moment you throw some object into space, you can think that you have thrown it into a pump where there is the pumping capacity is infinite. So whatever is there can be sucked out. Exponential decrease in pressure with altitude and increase in mean free path with altitude, and okay, the relations are here. So effects wise, yeah, cold shoulders, variation of electrical parameters with temperature. That's why an amplifier you design for a gain, particular gain of 10, you say it may be 12 in hot or it may be 8 in cold or vice versa. Cold start problems, even we all know, even our scooter will not start if you are having a cold season, correct? So but then if you are seeing the temperatures of whatever minus 100 degrees, it is definitely not my motors are. So that's why you need to have thermal control. Differential expansion and contraction joints of dissimilar metals. Changes in frictional characteristics will happen due to temperature. And in electronics, increased failures. Okay, the failure rate, even we if it get heated very fast, we get all kinds of diseases, correct? So that is the result of thermal impact. So the life will come down with respect to electrical. That is the reaction, the Arrhenius reaction rate model is there, so which will describe the impact of life with the temperature. And temperature, so there are various, most important aspect is thermal design has to be proper to maintain the subsystems under safe operating limits. And derating, so what we do is, if a component is rated for 1 watt, we will be using it for half watt only. If it is a 200 volts capacitor, use it for 100 volts. This is to extend the life. And temperature compensation provision for sensitive elements, design qualification to ensure margins. These are, so what we do is the qualification model will be built where we will overestimated temperatures, you give sufficient margin and test so that the design margins are ensured. And simulations wise, thermal and vacuum combined way can be tested in thermal vacuum test. But in vacuum, as I told, it can go to 10 power minus 12 torr also. Simulating that kind of, because mean free path is, we told 500 meters or much more. So how do you simulate in a finite chamber of half meter size? You cannot simulate this kind of mean free path. So even 10 power minus 4 torr or 10 power minus 5 torr, we are able to simulate on the ground. So that if we are able to do most practical applications, that is adequate. And thermal balance test is done to evaluate that our thermal design is correct. Under thermal balance, what we do is one side we simulate sun, solar radiation, another side we simulate Earth's albedo, another side we put solar is done by a xenon arc lamp simulator. And also we do the spacecraft itself will be going through summer solstice, winter solstice, equinox and all those things. So for all of those aspects, to simulate that, spacecraft will be rotated to simulate the angle, okay, between the orbital plane and the equatorial plane, whatever angle is there. So that will be, and the sun angle also. Sun will be changing even every day. If we dry our clothes, we know sometimes sound will come this side, sometimes south, sometimes north. Slowly it will be drifting. So that will all change the thermal design. No? So that for simulating that motion, the spacecraft will be mounted on a rate table and the required angles are given to various, to create various seasons for testing. And special test requirements are there for star sensor and static earth sensor, and standard outgassing test for materials. These are all done. Then we talked of temperature, we talked of vacuum, we talked about weightlessness. Then now we are coming to the particles. There is a neutral environment. Contributing factors are neutral atmospheric density. At low Earth orbit, it will be 10 to the power of 15 oxygen atoms per meter cube. Okay. High orbital velocity, though they are oxygen atoms, so size may be small, but they are having a, so kinetic energy will be there. 8 kilometers per second orbital velocity will be there for those particles. And large number of collisions will be happening between them with ambient atoms. And that will be 3 into 10 power 22 collisions per hour per 1 square meter of spacecraft. So they are constantly impending on the spacecraft outer surfaces. Okay, so this is significant in low Earth orbits. And atomic oxygen, so that is a very, very corrosive material. So that element, okay, atomic oxygen. So it is prevalent up to 650 kilometers, and it's a function of solar cycle. Solar cycle, I think people will be knowing. So solar sun has got a cycle of 11 years approximately. So the environment, the sun intensity or whatever its own ferocity will be changing as a function of solar cycle. So depending on which part of cycle we are. So above 650 kilometers is less, but especially around 400-500 kilometers. That's why we don't keep those things. Atomic oxygen effect will have a very severe impact on the solar panels and all. So effects wise, aerodynamic drag, as they are particles which are constantly impinging, they causes orbital decay and it will slowly degrade it will come back to Earth's atmosphere sooner. Material erosion due to sputtering, material degradation due to atomic oxygen attack, especially silver coating and Kapton, these things are done to overcome those things. But silver as such is it can get a very fast reaction. So alteration of thermal properties, solar array interconnects, they get eroded. So visible glow also, sometimes you can see payload performance, visibly you can see a glow. So mitigating techniques, of course, material selection has to consider atomic oxygen resistance, glow characteristics, sputtering thresholds, configuration to minimize the drag by flying the vehicle. So dynamically, aerodynamics, you have to design such that the impact of these particles on the drag is due to the drag is minimized. So the whatever is that force, whatever the direction of this particle impingement is there, to that you would fly with a different angle so that the impact is minimized. And orient sensitive surfaces and optical sensors away from RAM. Use of protective coatings, of course, and choosing of orbit to minimize effects. So proper sizing of propulsion and control elements to take care of these impacts. These are all the mitigating techniques. So how to simulate a neutral environment? Theoretical analysis for expected mission profile is one aspect, and atomic oxygen impact test can be done in a limited controlled conditions. One is theoretical, and accelerate some electron particle accelerators can be used to create that because of the kinetic energy. You should create these kind of 5 eV energies associated with orbital impact. So particle accelerators are used. This is at a material level. Total spacecraft or equipment cannot be tested. At material levels, these studies can be done. So we talked all this orbital that was neutral. It was not having any charge. But now we are moving from neutral environment to the plasma. Plasma is produced by heating of a gas. When an atomic electron receives enough energy to escape electrical attraction to nucleus, this produces mixture of negatively charged electrons and positively charged atoms. So you are having ions here. So produced by photoionization, solar, ultraviolet, whatever UV is there in solar spectrum. So that will be causing the ambient neutrals and by transport from other regions. And it's also a result of geomagnetic storms. Plasma can be defined as a gas of electrically charged particles in which potential energy of attraction between a typical particle and its nearest neighbor is smaller than its kinetic energy. So this is how the plasma is produced. And if kinetic energy is less, they recombine, establishing neutrality. But 99% of the universe is plasma. During geomagnetic storms, higher energy plasma is encountered between midnight and 6 a.m. So spacecraft orbit, that's what I told. Earlier I told effect electrostatic charge on ground, like handles also with dry places. If you go to other Western countries and all, where humidity is not there, we can see if you touch a handle also, unless it is grounded, we can get an electric shock. Our clothes, when we take out, that is a very normal thing, that our hair, you can get a shock. So that is on the ground. Okay, that is a turboelectric effect. But here it is spacecraft charging is here. This is due to buildup of the potential, because the surfaces are dielectric, outside surfaces, and these charged particles are impinging on that. So the outer surfaces, they get potential will go up, and it can result up to 20,000 volts in geo. Here it is a potential difference. Why the potential difference comes? When the surfaces are not equipotential, that means they are not conductive. If you are having a perfect, say, metal sheet outside a spacecraft, then there is no problem, because all the charge will be uniformly distributed. Even if it is 100,000 volts, no problem. Like crows we see, they will be safe on an electric wire till they touch the second wire. Right? Only when it touches neutral, it will get dyed. Correct? So as long as it is equipotential, no problem, whatever be the charge. But that is not possible because we use all kinds of surfaces on the spacecraft. So there can be differential charges produced. Once there is a differential, electric arcing can happen. That is where electrostatic discharge will happen, and that arcing will produce in such high currents which can kill the electronics inside the spacecraft. So the charge buildup can induce greater drag. It can accelerate ions to surface, increasing sputtering rate. Most important, ESD between regions of different potentials, which can lead to arcing due to dielectric breakdown or gaseous discharge. Then material damage, electromagnetic interference effects, devices. Nowadays, microelectronics is so small. The devices have gone below micron level, submicron level. So the devices can easily get impacted due to the effects of the electrostatic discharge. So plasma on orbit, if you take how to mitigate is make exterior surfaces of uniform conductivity if possible, because there are some all not possible. Then what we put is some buttons buttons will keep, and grounding outside you have to intentionally create some small buttons and connect all of them through a wire or something like that, so that outside things will get neutralized. The whatever plasma is getting impinged, the differences in potential are avoided. And grounding, EMI shielding and filtering for all electronic circuitry, and active current balance by a plasma contractor. This is an active method. Other things are passive. Here you produce some active techniques you can use, or grounding of all unused wires. Simply one wire without grounding, if you leave it floating, this can spoil the equipment inside. Okay, we saw this ourselves. We have faced in our first communication satellite INSAT 2A. A big instrument like VHR was one floating wire was there. Later we traced that was affecting control system performance. Okay, so ESD testing wise, there are different testing. There are equipment available to create ESD, radiated discharge, single point discharge, structural current discharge. I'm not going to explain what of them, but there are methods available which you can create and test for these factors. Then comes the particulate radiation. Here these are particles. Earlier talking about charged environment. Here these are the particles. Trapped particles are there, something called Van Allen belts in particular height and between certain latitudes or longitudes. So that is called Van Allen belts. The name is given by the inventor of those belts. So trapped particles are there. There are high energy particles, solar protons. They are having very high energy. Cosmic rays, which are from galactic origin, from where they are coming, from distant stars and all that. Solar wind itself is there. And low energy charged particles, which are trapped in geomagnetic field. And there is a very specific atmosphere, this one called South Atlantic anomaly. So that is another thing which is having an anomalous region where these particles are much higher densities. Okay, like typical characteristics are, it consists of energetic charged particles. They are having energy and charge also. Electrons, protons, neutrons, heavier ions and photons. All the types of things are there. X-ray, gamma rays can penetrate through surface layer in the material underneath. Even if you are having some surface like aluminum box, still they can penetrate through that also, because they are having lots of energy. The energy level flux are highly dependent on orbital height, location, time, and the measurement is in rads. We call type of radiation, kilorads, like radiation per second, like that. So 1 rad is 0.01 joules per kg. Type of radiation, dose rate, total dose, damage threshold. So when a particular, we build what is called radiation hardened electronic devices. So they will be very expensive. Just to give an example, a normal FPGA may cost a few hundreds or thousands of rupees if you think. If it is radiation hardened, it will cost 25 lakhs. 25 lakhs versus 25,000 or whatever. Okay. So that is the type of cost difference that is there when they get radiation hardened, because the quantities are less, the consumption is less, one part. And here the thing has to start from the wafer level. So you have to have a separate line for producing these quantities. Were very small quantities for producing these devices, but you need to have a separate fab. So that's why it becomes so expensive. And effects on the spacecraft hardware are solar cell degradation, electronic parts, material degradation, single event effects. What we call is suddenly when a particle passes through these devices, like RAM and all, memory devices, there one particular location will state change will happen. But if that particular location happens to be having some software code, so your program can misbehave. So then how memory error in avionics affects on living matter, ability of cell to see. Human beings also, you would have read a lot nowadays with all the people going there. So there is impact of radiation on human health also. So mitigating how you do, one is radiation shielding. There are some materials like lead which will be absorbing the radiation much more effectively than other steel or something like that. So even a small thickness will be able to, but penalty will be the weight. Use of rad-hard devices with specified total dose. Here the penalty is of course cost. And there are other things to avoid software failures due to the memory corruption. We are having majority voting, error detection and correction, watchdog timer, safety logics. Problem of EDAC and all is, or majority voting, if you want to put, you have to put majority voting is 2 out of 3 you have to compare and take a decision. Then your hardware is, if one is needed, because you have put majority voting, it has to be tripled. So the devices, the hardware will be tripling. So that is the kind of impact. But if you have to survive for 15 years, you have to do that. That's why space systems become so expensive. Practical examples, okay, I'll skip this. Particulate radiation Then how do you simulate? There are AI. We go to Kidwai actually, because for cancer research they will be doing a lot of radiation sources and all. So we go there and do some of our hardware, not at full level, but at component level we can go to Kidwai. But to get that facility is quite involved, because there is always medical research, so much is going on. So to get and book a facility is not going to be easy. Then proton or heavy ion bombardment using Van de Graaff generator at Nuclear Science Center. So there are methods. Then micrometeoroids and space debris. Okay, this is micrometeoroids is natural. Okay, nothing you can do. They are there. Space debris is man-made. So how we have to do? Breakup of comets, asteroids, leftover pieces of non-operational spacecraft, boost stages. Even rockets, once they go out of sphere of influence of Earth, the stages are still floating, maybe for 1 month or 15 days, 20 days. Till then it is a debris. It is an environment. If you are launching another spacecraft, it may hit it. Okay, and the least launch vehicle. So that's why there are methods to, characteristics are there, quite small, even as very erosion of surface materials. The problem is the smallest particle also, because of the kinetic energy, it can kill the things. There was in shuttle, there was a window was made a hole by 1 mm or less than that particle, like that. So thermal control properties, all these aspects will happen. Up to 0.1 mm, thermal blankets or structural panels can take care. But beyond that, it's difficult. Orientation of sensitive surfaces away from RAM, Leonid shower, like that. When it happens, our spacecraft centers, we will be doing the operations on the spacecraft to move them away from the most predicted zone. And choice of orbit is important. Shielding by bumper on the leading edge of this will not be done for regular spacecrafts, but for human space missions and all, because life is involved. So that shielding is there. Avoid using single stage to orbit boosters. These are guidelines. Okay, these are all conventions. Whether people follow or not, China they don't follow. Okay, longer life satellites, so that debris will come down. Venting fuel tanks at the end of mission. Venting means removing the fuel. If you keep the fuel, then the probability of it gets bursting in the orbit is more. So if that bursts, then a lot of space debris is created. So now internationally conventions, and they are not enforceable, but people have to voluntarily do this, because it is for each other's welfare. It's anybody's problem is problem only. Okay, so deorbiting after life, these are all the guidelines which are coming slowly, and slowly as the impact is understood, people are also following. And space law to address debris problem, but it's like you all know how much International Court of Justice can influence anybody. So that's there. So practically 27 windows were damaged in 8 flights of shuttle in 30 missions. On STS-7, a 0.2 mm diameter fleck of paint, 0.2 mm fleck of paint has impacted a side window. Cost of refurbishment was $50,000. So this is some book I have taken. Simulation and evaluation methodology, hypervelocity impact studies, Van de Graaff accelerator. So that you can see the level of acceleration achieved, 40 kilometers per second on a particle of 10 power minus 10 grams. I don't know how they do it, but there are equipment available to do that. Larger masses are accelerated through light gas guns. Study of shock wave propagation by numerical methods. Impact probability studies. Models are available for estimating the flux. Then magnetic field, as you go away, as I told, inverse square law makes it lesser and lesser. But in geosynchronous orbit at 36,000 kilometers also, we can use that positively actually. Within the spacecraft, we should use magnetically clean materials, but elsewhere we use it for control of the spacecraft, because residual magnetic field is there. One magnetic torquer will be there through which we pass the current, and that will interact with the Earth's magnetic field and produces a couple which turns the spacecraft, because the disturbances are, the forces are less. So that's why even a small electric field is sufficient to maneuver the spacecraft. Then pre-launch, I think I'm getting closer to the time, so I won't explain much, but yes, on ground we are having particles are there and ambient so contamination control is one important thing. And electrostatic discharge, ESD. Even if you touch an electronic device, it will die without doing anything. You just hand touch. If you are carrying electrostatic discharge on your own body, because it can be kilovolts, so that can kill the electronic device. So for that we have got some ESD specific precautions are there. We have to ensure that before we enter, the charge which is there on our own body is grounded. So all the handles, the floor on which we walk, and the tables which are assembling the electronic equipment, all of them AST precautions are taken, and equipotential mats and all are put, so that anything is there, it is conductive. Conductive means not metal plate, that will be very fast. So there are some ranges. Okay, what is the conductivity? So accordingly resistivity. So as per that, you will be pleading the charges that are there, so that the equipment that we are handling is safe. Humidity is the worst environment. That is the only good thing in space because there is no humidity. Otherwise, in most of our household equipment will go bad due to the humidity. Sea coast, if you go, it is still worse because humidity is having that salinity also. So because of that. So at the time of fabrication, testing, storage, environmental facilities and all, we do some humidity control also. So that is important. And it is more difficult to do it in coastal places and all. So the expenses will be involved. Effects on space hardware will be, of course, I will not elaborate too much. Same way electrostatic discharge I have already told. And dynamic environment is one thing. During launch phase, we are having transportation is there. That is compared to a launch vehicle induced dynamic environment, transportation, it is less. Of course, Bangalore potholes, anything can happen. Launch phase loads are acceleration transmitted through launch vehicle interface, and direct acoustic noise is through the shroud, and shock is during events triggered by pyrotechnics like stage separations. Spacecraft separation is the most important trigger for the shock. And acoustic noise is generated by sources such as rocket engine exhaust noise, boundary layer turbulence, base pressure fluctuations, and oscillating shock waves. Actually, it's not my area, so I'm only reading here. Its predominant characteristics are frequency distribution and spatial distribution. How it gets propagated over the entire vehicle or entire spacecraft. Okay, so those are the things which have to be studied. Then random vibration, sine vibration, shock, all these effects are there. Of course, vibration impact is very well known. It can cause mechanical damage to components units. Even before you launch you inject the spacecraft into orbit, the damage would have been done if it is not designed to withstand that dynamic environment. So we have to design for predicted loads, we have to qualify, we have to test, and some sensitive components due to vibration, if they are there, we have to what we call as spotting. That is basically some adhesive kind of thing is there to arrest them during the launch phase. And snubbers are vibration isolators for very, very selected items where you cannot, other techniques are not useful. So, but design of an vibration isolator itself is a very challenging thing. In the simulation, what we have to do is spacecraft mathematical model is given to launch vehicle people. They combine launch vehicle mathematical model with spacecraft mathematical model and predict the loads that are going to be faced at various sites of the spacecraft. On each panel, at each location, what are the expected dynamic loads? Launch vehicle team will marry the spacecraft mathematical model and then the launch vehicle mathematical model. Based on that, they predict the levels and give, and the individual equipment have to be tested with the margins for the predicted environment.
Sir, namaste, sir. Sir, with this kind of environment in space, the reuse of vehicles, how expensive it is, and what are the things we are doing on that reuse of space vehicles, sir?
The reuse is mainly with respect to the launch vehicles. Launch vehicles are not going to see any of this environment. Okay, whatever I told on orbit, they see launch phase and pre-launch. But after launch, it is going to come back much before. Within half an hour, it is coming back. Whatever on-orbit environment I have told is for 15 years. Okay, so there the question of reuse is right now not there. But the reuse is only soon after launch, the first stage mainly. The first stage, within minutes it will come back. Okay, there you don't want to lose the rocket shell, no, total that structure and all those things. Only the fuel is spent, rest of the things are alive. So those things you are trying to. So there the important part is re-entry. The most difficult portion of reuse is the re-entry of the vehicle, because during re-entry it is going to see a lot of heat, no, when it enters its atmosphere back. When it is entering, it is having a tremendous kinetic energy passing through the atmosphere that produces some thousands of degrees of centigrade. So that's why what they do is there the heat sheet, this what we call ablatives, the use of ablatives and all that is there to see that the inside things are not impacted due to the re-entry. So reuse with respect to our own thing, we have not at very, very elementary level. We have done RLV, reusable launch vehicle, some demo flights and all, but they are at much elementary level. Even in the whole world also, till 1 or 2 months back, it was only SpaceX who could do the re-entry, or reuse, sorry, not re-entry. Re-entry is different, that they are doing all the manned missions to re-enter. But SpaceX was the only thing which was able to come back and land and like that. Recently, Jeff Bezos thing, this Blue Origin, they also have demonstrated one vehicle where they could come back safely. Okay, so reuse is not for spacecraft, that atmosphere thing. But we have done one SRE, spacecraft recovery experiment like that, where after some time it has come back. So there, as I told, ablatives is the main thing which has to withstand the re-entry heat. afterwards it can be used. Otherwise, in-orbit repair also is another aspect for reuse. Two things need for extension of spacecraft life. One is once the propellant is over. Okay, if the propellant is over, you have to refill. Okay, nowadays people are experimenting and successfully demonstrated also. So you have some standard interfaces where another module which is having a fuel can be launched, say 1 year before the life is going to be extended. It goes and docks to the existing spacecraft with a fuel tank. Okay, so at towards end, after 10 or 15 years, you launch one more, and this tank will go and dock to the existing one. That way, successfully you can extend the life of the spacecraft. But whether your payload is useful after 15 years plus another 15-year extension after till 30 years on the ground and in orbit spacecraft, are they compatible? Are those technologies relevant? These are the other practical aspects of this. But otherwise, even small repairs also, like space station, if you take in orbit repair, that is another way by which you are able to replace the units.